All right. So let's see if we can just figure out a torque. Okay, so let's consider a yo-yo that's in the XY plane. And the string is wound around this inner cylinder. And you're pulling up on the string with a force of magnitude 0.6 newtons. What is the direction of the torque you're exerting on the yo-yo? Okay, that doesn't look too unanimous. So what's the issue here? Let's talk about it. What's confusing about this problem? Well, the yo-yo may or may not turn. I mean, yes, presumably you're gonna change its angular momentum by exerting a torque on it for some period. But the question is, in order to find out what you're doing to its angular momentum, you definitely need to figure out the torque. And does the torque have anything to do with it? Does the torque depend on its current angular momentum? No, it's just like a force, right? I mean, you can exert something can have momentum or not momentum. You exert a force on it. The force is what you exert. It'll change its momentum, but it doesn't depend on its current momentum. So this torque, does the torque depend on the angular momentum of the yo-yo? No. Okay. So it presumably will change the angular momentum of the yo-yo if it acts long enough. So what's confusing about this situation? Okay, so here's the yo-yo. There's the string. You're pulling up. So what's the location about which we want to consider torque? The center. So we're interested in that location there. So what's the problem? The force is up, right? So there's F. Well, what's the definition of R? It's a vector going from what to what? So it goes to the point where the force is applied. Remember our picture of the wrench. And it starts at the location that you want to consider the angular momentum around, which may well be the center of mass. It isn't always, but it may well be. So how would I draw R? Okay, so we want to draw R. So that's R sub A, that's location A. So now can we find the angle between R and F? You want to try this again? Okay, so here's the question, and this is what we need to know. When you're using your hand to find the direction, are you going from F to R or R to F? And how do you know that? Yeah, because it's not commutative, and things you start with whatever the first we keep talking about the first vector and the second vector. We're talking about the order of vectors in the cross product, right? So the rule is you point your fingers along vector number 1, and then fold them toward vector number 2. So we better draw these vectors tail to tail, hadn't we? So that's R and yeah, so R goes to the point of application of the force. Now there may be something to talk about that here. So here's F. Okay, so you need to either mentally or physically do that, right, in order to, okay, so we got it? Okay. Okay, so that looks like positive Z. So let's see if we agree. So we point our fingers along R, and then we discover that we're going to have to break our wrist. So we rotate the wrist, curl fingers toward F, thumb sticks out, direction of positive Z, and the only thing we have to remember is to use the right hand. Okay. Now, what's the magnitude of the torque that you're exerting? So we have some numbers. This distance here, that's 0.00, it's 5 millimeters, 0.005 meters. This radius, that's 0.035 meters. You're pulling up with a force of 0.6 newtons. So what's the magnitude of the torque? Okay, so the question is are we talking about this vector for R or that vector for R, or does it matter? So the question is really, are we talking about the yo-yo plus the string being the system and you're exerting the force, in which case it's there? Or are we talking about the yo-yo being system and you plus the string are the surroundings, in which case the string is acting there? And you're thinking that probably you better get the same answer no matter how you do it, right? And that's correct. And so let's think about why. Let's think about why that is. First of all, you said the direction of the torque was going to be in the plus Z direction, right? So all we need to worry about is calculating the Z component of the torque, because we've just decided that the X and Y components are 0, right? So we don't need to bother with that. So let's think about how we might do that. So we want the Z component of the torque, and what would that look like in terms of all those X's and Y's that we multiply out and subtract to get the cross product? We have X, Y, Z. We want the Z component, so that looks like we have, okay, so we have Rx F sub Y here minus Ry F sub X, right? That would give us the torque. So let's use this. Okay, let's think about this. So what's the X component of this vector R? Okay, so that we know that's 0.005 meters. And what's the Y component of the force? 0.6 newtons. And now we have to subtract the y component of r, which we don't know because we didn't tell you how long the string was. But what's the x component of the force? 0. So in fact, it turns out to be only this component of r that's actually perpendicular to the force that actually mattered. So in that case, we get, what do we get? What's the answer there? Okay, so let's see what you said. You say that is 0.003 Newton meters, so that's right. So, and we would have gotten the same answer if we'd said the force was applied here, and because it only turned out to be the component of r perpendicular to this force that matters. So we can actually write this way. We can write the magnitude of the torque around location A is, we know that that's the magnitude of r times the magnitude of F times the sine of the angle. But it turns out that this piece, RA sine of theta, is really the component of r perpendicular to F. So we could express this vector r as the sum of that vector and that vector. So that's perpendicular and that's a parallel, and it's the perpendicular one, so we can rewrite that as the perpendicular distance times the magnitude of the force. Okay? So it works out the same either way. No, I'm saying that we are doing the following little algebraic move. We're saying, we're just rearranging terms here, so we have RA sine of theta F, and we're saying that that quantity is actually the perpendicular distance. So we can rewrite this whole thing as r perpendicular magnitude of F. This may be the clearest way to see it, because it turned out that this y distance, the distance parallel to the force, just didn't matter. And only the distance perpendicular to the force gave you a non-zero value, which means that you could exert this force here or here or here or here or here or here, and you'd still be getting the same torque. Okay? All right. And of course, that actually is going to turn out to be true for angular momentum also, because that's a cross product as well. So if it's only the component of r that's perpendicular to F that matters, then it's going to be the component of r that's perpendicular to the momentum that matters in the translational angular momentum, magnitude of translational angular momentum. Okay.